Okay, this video will be going through question 6 of your work energy power tutorial. Okay, figure 6 shows part of a hydroelectric system that generates electricity from flowing water. So basically, the flowing water will hit the turbine and make the turbine turn. The blades will turn. Turbine will turn. So the turbine, when it turns, it is moving. So it's going to be having energy in the kinetic store. So this turning effect will then cause the generator to generate electricity. Okay. So every minute, take note, this is minute, water with a total kinetic energy of 14 kilojoules hits the turbine blades, causing it to rotate. The rotating axis transfers half of the water's kinetic energy to the generator. So the generator will be getting 7,000 joules of 7 kilojoules. Okay, so describe how the flowing water does work on the turbine blades. Now, what is the definition of doing work? That means the object must move in the direction of the force. Okay, there must be movement in the direction of the force. So let's see how we can answer this question. Okay, so the observation is that as the water hits the blade, it exerts a force on the blade, right? So one of the requirements for work to be done is that there must be a force, right? So it exerts a force on the blade, pushing the blade in the same direction. So the blade will actually move, right? So the law is that as work done is a product of the force applied. So one thing is you need the force, and you need to multiply it to the distance moved by the object in the same direction as the force. Okay, so it has hit both criteria, therefore there's work done. Okay, so the explanation is that as the turbine blade moves in the direction of the force, the work is done by the water on the blade. So you actually just need this. Okay, you need everything, because now this is a describing question. So you need to describe what you have observed, because the water hits the blade, exerts a force on the blade, pushing the blade in the same direction. Then you bring in the law, which is actually the work done is the product of the force and the distance moved in the direction of the force. And the explanation is that you apply to the context. Okay, you apply to the context. So this is applying to the context. Next, calculate the power input to the generator. So power is actually work done over time. Okay, so the work done is actually the energy that is being transferred, which is 7,000 joules. Oh, sorry, they're asking for the power input, so I shouldn't be using 7,000 joules. I should be using 14,000 joules, because this is the energy of the water, right? And it transfers, and this water actually has kinetic energy of 14,000 joules. So this is the input energy. Okay, the energy that's hitting the turbine. So the time is actually 60 minutes. Okay, so I have to change, not 60 minutes, it's actually 1 minute. I'm sorry, it's 1 minute every minute. So I need to convert it to SI unit of seconds. So it will be value of 233 watts. Okay, so this is the power by the water. But what is the power to the generator? The power by the generator is that it transfers only half. Okay, the rotating axis only transfers half. So the power to generator is actually half of that. So equals to 233 divided by 2 equals to 117 watts. Okay, remember the unit for power. Now, electrical power output from the generator is measured to be 100 watts. So this is what is being measured. Theoretically, it is 117. Okay, but however, when we measure it, it is only 100 watts. So it's actually less than what we have calculated. So explain why the electrical power output is different from your answer in part B. Let's see how we can answer. Okay, due to dissipative forces within the generator. So what are all these dissipative forces? There can be friction, because in the moving parts. Okay. There is also, because it's by electrical pathway, there's some electrical resistance. You learn in Sec 2, right? There's also resistance, right? So there's resistance, electrical resistance. So all these are the dissipative forces. And it happens within the generator because the water actually transfers 14,000 kilojoules, but the turbine, the moving parts, only transferred 7,000 joules to the generator. Okay, so by right, I should have 117 watts. But this is further reduced to 100 watts because of all these dissipative forces within the generator. So some of this energy input is transferred to the internal store of the generator. You'll find that the generator will actually becomes warmer, okay? And of course, some of this energy will also be transferred to the surrounding, okay? So these are actually the non-useful energy output, right? We have no choice because of all these dissipative forces, the generator will become hot, and when it's hot, some of this energy will be transferred to the surrounding as well. Therefore, there's less useful energy output per unit time, which is actually lesser power. Okay? Okay, let's go through the last question, question 7. Now, figure 7 shows an electric motor and a pulley system used to pull a 180 kg load. So this is again mass. Okay. So this mass of 180 kg is actually pulled onto a truck. In order to pull the load up the ramp at a steady speed, the electric motor pulls the cable with a tension of 600 Newton. So this 600 Newton is exerted on this load. However, if you think about it, this load is 180 kg. So actually the weight, if it's 180 kg, the weight is actually 1800 Newton. Okay, so I only need to exert 600 Newton pulling force, and I can bring this mass of 180 kg up this ramp, up to this point here. Okay, so shall we calculate the changes in the energy? Okay, they at first want us to describe the changes in energy as the load is being pulled up the ramp. Okay. Okay, describe the changes in energy as the load is being pulled up the ramp. So maybe it's the changes in energy in this isolated system, right? The electric motor does work on the load to transfer energy mechanically to the gravitational potential store of the load, because at first it was at the bottom of this slope. It is now being pulled up to the top of the slope, which has a height of 1 meter. So of course there's energy being transferred to the gravitational potential store of the load, okay, and to the internal store of the load and its surrounding. Why? Because the question didn't say that the slope is frictionless. So as it's moving up, we have to do work against friction, right? So when we do work against friction, there is usually energy transferred to the internal store of the load, and if the load heats up, higher temperature, it will also transfer some of the energy to the internal store of the surrounding. Okay, you may want to play this back again, or maybe I just repeat. So we start off with the electric motor doing work on the load, right? Because it's pulling the load up with a force, and the load moves in the direction of the force. Therefore, there's work done on the load, and this is by mechanical method. So this is the mechanical pathway. And what is this energy that's being transferred to the load? It is being transferred to the gravitational potential store. Now you may say, how about the kinetic store? Because actually the load is moving. So over here, it pulls it up at a steady speed. Okay, that means there's no change in the speed. So there is no change to the the energy in the kinetic store. Okay. So but then we talk about there could be friction on the slope, because the question didn't say that it's a smooth slope or ignoring friction. Therefore, as the load brushes against the rough surface, right, there will be some energy needed to do work against friction. Okay, needed to do work against friction, and therefore some of the energy from the electric motor will then be transferred to the internal store of the load. Internal store is basically heat or thermal energy. Okay, so it goes to the internal store of the load and also to the surrounding. The surrounding will also be heated up, right? This is due to work done against friction between the ram and the load. Then this was the point that I talked about it just now. There is no energy transferred to the kinetic store as the load is move at a constant speed, because they are asking us to describe the changes in energy. So there's actually no energy transferred to the kinetic store. Okay, so B part 1, calculate the work done by the tension. So it's actually a force in pulling the load up the ramp. So the tension is in this direction, diagonal, a value of 600 Newton. So work done is actually force times distance moved in the direction of the force. So we should choose 4 meters and not the 1 meter. So the work done is actually force times distance moved in the direction of the force. The force is 600 multiplied by 4. The energy or work done is actually 2400 joules. Okay, so they say state the amount of electrical energy used by the electric motor. So it will also be 2400 joules, because they say hence and state, right? So C1, determine the work done against friction. How do we know that there's friction? Now, I was talking about this just now. What if I didn't use the electric motor? Okay, this part is very important because the slope kind of question always baffles students during test and exam, right? So, what happens if I don't use this electric motor and I don't use this pulley system? Okay, the load itself is 180 kg. Okay, that means it has a force of a weight of 1800 newtons, right? By using W equals to mg, the weight is going to be 1800 newtons. So 1800 newtons or 180 kg, can anyone just lift it up to this point by their bare hands without using machine? The idea is not really possible, right? Because it's already 180 kg. Okay, some of you may be doing deadlift. I don't think you can do 180 kg. Somehow you have to lift it up to the height of 1 meter. But if there really is somebody who can do it, 180 kg, you have to lift the load up with a force of 1800 Newton and the vertical height of 1 meter. The work done in lifting this up will then be 1800 multiplied by 1. So the work done is actually 1800 joules, and this will go into the energy in the gravitational potential store, right? So why is it that with this 1800 joules I can lift it up a height of 1 meter? Why is it that I need a amount of 2400 joules to lift it up by the ram? Okay, so of course in the ram there is friction. So the 2400 joules, subtract away the 1800 joules. This is the work done against friction. Okay, so we are actually using 600 joules to do work against friction. Then somebody might say, why don't we just lift it up? So like what I explained just now, this is actually a mass of 180 kg. It's very massive. So that's why we have to use the slope to help us. So you see, even though using the slope requires more energy, okay, because there's friction involved, however, I can actually lift up this slope, lift up the load easily to this point, okay, because the force needed is 600 Newton versus the force of 1800 Newtons. Okay, so now that we have calculated the work done against friction, so we can then calculate the frictional force, okay, assuming that the frictional force is constant. So work done is actually equals to force times distance moved in the direction of the force, and we have established that the work done against friction is 600 joules. So the force is what we want to find, and actually the distance is 4 in the direction of the force. So the frictional force is a value of 150 newtons. Okay. Part D, electric power input to the electric motor is 400 watts. So this is the power that is input. Calculate the time taken to pull the load up. So just now we have established that the work done is actually 2,400. Okay, and sorry, maybe I do this here, and the power is 400, so equals to 2,400 over T, and then this T will actually be over 400, so equals to 6 seconds. Okay, so this is the answer, the time taken to pull the load up the slope. Okay, so this slope question is actually quite important, because sometimes there's friction and it results in the total energy that move up vertically, and by the slope the total energy may be different because there's friction. Okay, yeah.